All right, so thanks everyone for being back on time. Now we come to the second part of the morning session, and our first speaker is Alfonso, Chacon. And he's going to talk about skills, ability, and trial tactics.
I want to start by making a discussion of regulating the organization, what's making very and fun. And yeah, as it was mentioned, I will talk about strength, stability, and chiral methods. Specifically, what I want to show you is some experiments that we performed using small-angle neutron scattering, the iron-silicide compounds, and also some large system microscopy performed by the So I've not seen this base scatter as often as we used to inside the process, which is probably good. But I just want to review it very quickly. We already saw this in the last talk again. This typical base diagram is called chiral magnets. Arises from the interplay of these three different energy scales. And the pocket phase of the Skyrmion lattice is actually stabilized by the fluctuations, as we heard already yesterday. Indeed, however, we're not bound by this small phase in small pocket in the space diagram, but rather already very early in our studies, by 2010, it was the work of Alfonso from our team doing neutron scattering experiments that realized that over the 20% of iron silicide, you can get a Skyrmion lattice of low temperatures by following the right treatment, you can say. So if you take this compound, regardless of the direction you apply the field along, if you go through superficial cold, you observe the typical helical transition, which in this case is very high in comparison to HC2, so it shows that the system should possess very strong magnetic crystalline isotropes, and at some point you reach this Skyrmion lattice phase, which is also very strongly independent of the crystal direction you apply the field along. However, if you then start at above the critical temperature, apply the field, and pull slowly through the Skyrmion lattice, depending on the direction of the field, you can stabilize the Skyrmion lattice to the lowest temperatures. And, this is data you took with small-angle neutron scattering. And these are not, so metastable lattices have been gaining a lot of interest lately. This was the first publicized big phase diagram on one compound that shows the same type of metastability. So we don't need to hyper-cool these systems, but the only thing we need to do is go to the Skyrmion lattice, and just the normal cooling rate, as it was mentioned in the last talk, is enough to hyper-cool these lattices in a metastable state down to the lowest temperatures. And in this case of this compound, they observe some interesting structure transitions from the Skyrmion lattice. Now, as it was mentioned in the last talk, there are different ways you can stabilize the Skyrmion lattices. There's the work done in copper sonic, where we heard yesterday you can get a very large stable pocket phase by applying a crystal field, and you can also get a metastable Skyrmion lattice by pulling through the Skyrmion lattice field or pocket phase once you have applied a magnetical field. Or as we just heard before the break, if you apply a current pulse and hit the sample very quickly, you can also get a Skyrmion lattice to the lowest temperature. For our studies, we decided to stick with this iron silicide cobalt because it can very nicely engineer the transition temperature as well as the pitch length of the system, going from a couple of nanometers up to several hundred of nanometers, as well as going from very low temperature for the transition up to around 50 Kelvin. And that was important for us because allowing to metastably take the Skyrmion lattice down to the lowest temperature, regardless of the doping, gave us the possibility to perform the first magnetic force microscopy measurements on this compound. It was the work that Emil did, published a couple of years ago, And what you observe here, due to the large, in this case for 50% dope compound, you get about 90 nanometers or 100 nanometers pitch length, so the skyrmions are quite big. Due to the fact that we can go to lowest temperature, the purpose is also very good. And once we were there, we were able to actually see the skyrmions. The question was, okay, what happens if we just remove the field? So we took the field slowly out. We go to 10 millitesla, and these worm-like structures start appearing. And if you go to 0 millitesla, they just become larger, and we still have some skyrmions in there. So the next question, of course, was, can we see the dynamic of this? Is this a time scale that we can actually observe with this technique? So what we imagine here is that there are block points or monopoles going through the sample that sit skyrmions together and remove one of the blocks that the skyrmions carry. So in order to check whether we can see this dynamics in real time, or with the time resolution that we are allowed with this technique, we convert a sample at 20 millitesla down to 10 Kelvin, and we reduce the field to 0 millitesla. We have the worm-like structures again, and then we left the sample alone for 15 hours. And when we took the measurement again, what we realized is, okay, not really anything has happened. This is, we realize it's almost even the same structure. There's some movement, there's some changes, but as a whole, there's very, very little going on. So we realized that if this is happening at the lowest temperature, there must be a temperature at some point where the time scale matches the different techniques that we have to probe the system. So the idea is at some point to go to neutron scattering of this compound, but first we need to actually prepare or determine the phase diagram of this metastable state very thoroughly. So we go back and start doing magnetization and susceptibility experiments. So the typical signature that you will observe in these compounds when you take this measurement is a discrepancy between the real susceptibility, those are the full points, and the open points are the derivative of the magnetization. You will observe that at HC1, that's the transition from the helical phase to the conical phase. We understand this as the movement of large structures, of large phases, the reorientation of those leads to this discrepancy in those two signals, and the fact that those two signals probe different time scales in the system. And at the transition between the conical and the skyrmion lattice, you observe as well, again, the discrepancy in those two signatures, as well as a dissipative signature in the imaginary form. If we then cool the sample to those temperatures and do the same thing, but we also compare it when we come from a saturated state and just move through the whole phase diagram, we observe that the green curve is featureless. So that means that for this field direction, we don't get the helical propagation pattern. So this is not quite such a surprise, since we are applying the field along the 1/0 direction. This is the easy direction of the system, the helices are propagating along this direction. But this happens regardless of the direction the field is applied. So although, as I mentioned before, we have strong anisotropies, which are identified on the high HC1 compared to the transition between conical to permanent state HC2, the system for some reason does not relax back into the normal phase of propagation into this anisotropies. If we, so yeah, that's that part, but again, this is a special case where I want to observe direction. If we then pull the sample through the skyrmion lattice, that would be applying the field at 5 millitesla, and then pull the sample down to the lowest temperatures, we observe that if we increase the field, there is a discrepancy between the derivative of the magnetization, those are again the open points, and the susceptibility at about 28 to 30 millitesla, pointing to a transition from the skyrmion lattice, from the metastable skyrmion lattice, to something else. I say something else because in this case, this transition is higher to the point where we would normally identify the transition from the conical state to the permanent state. So, to some extent, what we can say is that it's very probable that this skyrmion lattice lives in a permanent background. If we reduce the field, the first important point is at 0 field we observe very remote mineralization. This is something that we won't expect from conical or helical domains or propagations. And then we see two discrepancies between the and the susceptibility, the first of which we identify as the creation of these worm-like structures of the skyrmions merging together and building some intermediate state to the helical state. And the second one would be the transition from the helical state to the conical state. So we confirm this this phase identification by doing small angle Newton scattering. So what you see here on the left is a typical scattering pattern that you obtain at zero field for this compound. As I said before, those are the 001 and 010, the 100 and the 010 propagations. Because since the easy axis is a 100 in this system, you get three different domains. If you apply the field, then you get a conical propagation. So there's no further signatures in this image. That means we have a single domain state all propagating along the field. If we look at the image perpendicular the magnetic field through the A phase at at low temperatures, what we get is a very nice skyrmion lattice. There's actually two domains here. The reason why the spots on top are somewhat brighter is because these images are the sum of the rocking scan along the vertical axis. So that allows more intensity to be summed up on those points. If we reduce the field and go to about -0.2 to 2, there still is a skyrmion lattice there. We start seeing less intensity on it. And as I will show you later, there will be also some intensity arising on all these points. If we increase the field up to 0.8 2, the skyrmion lattice is still there, so we're confirming that definitely the signals that we are observing in the magnetization are arising from this metastable skyrmion lattice that we're able to cool down by just the normal cooling procedures. So we go ahead and just take this type of measurements of the susceptibility and the derivative of magnetization at different temperatures, and what we end up with is these three different phase diagrams depending on the history of the sample. So if you come from zero fields, as typical phase diagram you observe everywhere, you have a quite high HC1, the HC2 transition to the ferromagnetic phase, and the skyrmion lattice just below C. If you come from the saturated phase, then you only see a conical propagation and a small skyrmion lattice just below C. And if we cool the sample through the skyrmion lattice and increase the field or decrease the field accordingly, then we observe a very large phase of metastable skyrmion lattice, as well as a transition to a helical phase starting from some critical temperature or critical field, as well as a conical phase, as we would typically expect. So, depending on whether we go, whether we increase the field, decrease the field, we would expect two different things based on what we observe in the magnetic phase microscopy, and just by what we expect from what we know of these phases. So at low fields, we expect the skyrmions to stick together, while at high fields, we would expect the skyrmions to be erased. And the transition to a conical or ferromagnetic state from the view of the skyrmions is practically the same. You just lose the skyrmion, and the structure will then twirl again if it is the conical phase. So in order to study this with small angle Newton scattering, we prepared a sample. This is the sample. Those are the dimensions of the sample, so it's 2.5 millimeters across. And we apply the field along one of the short axes in order to have a small amount of material that the Newtons have to go through, but increase the amount of material that we can eliminate. We make the measurements with these two configurations, applying the field parallel to the neutrons and applying the field perpendicular to the neutrons, so that we can observe both conical and helical as well as scattering propagation. So typically what we would expect to see are these scattering patterns. So here, the green dots belong to the skyrmion lattice. If it was a single phase state, we know that we have two phases, but just for the sake of cleanliness, we left those out. And what is important here is that the helical propagation of this plane overlaps with those two brackets belonging to the skyrmion lattice. So if we want to get some information on this helical phase, we will need to do some extra work. However, since we chose the field to zero direction, we can easily separate the signals of the conical phase, the helical phase, and the Skyrmion lattice in the configuration where the field is applied perpendicular to our income. So for our studies, we prepare the sample as mentioned before. We could always go to the Skyrmion lattice before deciding where exactly to plot the phase diagram. We performed different tests. We went through different fields, checked how much volume of Skyrmion lattice we obtain at those fields, and after defining what the optimal field is, then we pull down the sample again, go to zero field, and just wait, and measure it over time, every 5 or 30 seconds, depending on how much intensity we're getting. So this is the typical Skyrmion pattern that we have at that point. The 6 spots of Skyrmion lattice, the second somewhat weaker second domain, and if we reduce the field, what you get is this smearing out of the signal. That's probably just the reduction of the signal and the very low angular resolution that we have because of the very long pitch of this system. And what we can do is then separate the signal in those 3 components. So we have the Q1 and Q3 components of the Skyrmion lattice. Those should be helical clean. And the signal of the intensity for dose as a function of time looks like this. So that's at 25 Kelvin. And if we take the logarithm at the time, then we see that we have some linear behavior on it. So it seems to be that we have logarithmic dependence of time for the signal of the Skyrmion lattice. If we then look at the position where we have the overlapping of helical and Skyrmion lattice, we can separate those signals. Well, that's the signal both being separated, so that's the sum of both. And by norming data to the point of 9 millitesla, where all these 6 propagations show the same amount of intensity, so they should show the same behavior after reducing the field, we can extract the helical intensity. And when we observe this, that with increasing temperature, you have an increasing rate of decay, and at the same time, the increasing rate of intensity increasing in the helical phase. So we fit this data with this logarithmic function, since it's the easiest way to do it. There are other approaches as to how to work with this data. Stretch exponential is very often taken as a possibility. However, we feel, since we don't have a theory right now, there's no sense in trying to put more complicated bits into this data at this point. However, we do have an idea of why it is that we're seeing the logarithmic decay. We expect that to arise from a broad and flat distribution of activation energies, which are leading to these different times in the sample, where it's different lifetime for different Skyrmions in the sample, which integrated then with like a logarithmic. And if we try to make an approximation of what the width of this energy distribution would be, we turn out with 1000 Kelvin, which is huge and doesn't feel that good. But that's the data, and we cannot do a lot about it. So these are the decay rates that we obtain for different temperatures. So very interesting, as I showed you before in the phase diagram, there is a cut of 0 millitesla at around 7 Kelvin, which means that below that, the Skyrmion lattice is completely stable. If we do the same thing for increasing fields, then the situation is a bit easier. We don't need to separate the signals. I can tell you already that there's never signal at the helical positions. So even if the Skyrmion lattice decays into a helical propagation, it's always a helical propagation that is in the same plane as the Skyrmions were before. These are the intensities that we obtain at the conical phase. You see again, there's a transition into the conical phase, increase in the intensity of the Skyrmion lattice, and as I mentioned, no intensity at all in the helical phase. So here again, we observe a increased rate of decay or increasing fields. The signature is again very much logarithmic, and for the conical state, the signature is a bit more complicated, but here there are other effects that come into play regarding the intensity, and there's no point on norming the intensity to the starting value, since we are increasing it, there's no information. If we measure this for different fields, we see a stark asymmetry regarding the fields that we call the sample. So if we call normally at 9 millitesla, if we reduce the field, the skyrmion starts to decay almost immediately. While if we increase the field, there's at 20 Kelvin about a 50 millitesla needed before we observe any strong decay or immeasurable decay at all. This means that although we need to pull up 9 millitesla, this is not the main stability point or the main stable position for the skyrmion lattice in the phase diagram. And it also speaks to theoretical predictions that the energy barrier to the helical state should be lower than the energy barrier to the quantum state. So I want to summarize this part. We see a broad distribution of activation energies which lead to a lower rate of decay. There is a strong asymmetry between the higher and lower fields, pointing to the asymmetry of the phase diagram. And our main suspect right now for this broad activation energy are defect being either of the skyrmions themselves or of the monopoles of the system. So what we will do in this work, we start a collaboration with a group of Christian back in Regensburg. This is work that is right now submitted and waiting for replies. So anybody will reply to what we will reply. So we did exactly the same thing. This is a 230 nanometer example. It is cut from a single crystal, and the film is always applied along the thin axis. And at 35 Kelvin and 1.5 millitesla, we observe the typical helical lattice. The pitch limit is about the same. And at 35 Kelvin millitesla, the 23 millitesla is of course not corrected for the magnetization effects. We observe the skyrmion lattice. We can pull the sample down. The lowest temperature achievable in this setup is about 10 Kelvin, and we observe a very, very large area of skyrmion phase as expected. And as we did in the neutron scattering experiment, we go down to a certain temperature, we then increase or decrease the field, and mainly we studied these regions where the were lightly shaded with this pink color. And what you can observe if we decrease the field is a transition to the helical phase. Now we're able to actually observe single skyrmions merging over time. So the time resolution of this measurement is about 100 milliseconds. And if you concentrate on this area with the white rectangle, you see in the first picture there are 3 separate skyrmions, then the first merge, and then the third merge. If you look at other places on the image, there are merging going around at different places on the sample. We then count skyrmions over time, and this is the decay of the skyrmion number that we observe. And if we do the same thing going to higher fields, then you observe that this time there's no merging at all, but the skyrmions are just as high. The funny thing is, if you look at this red area, we observe that the skyrmion is not vanishing completely, but there is some reminiscent intensity there. And I will come back to that in just a moment. And again, we can count skyrmions, and maybe one needs to, it's important to know that just by changing the field, there's some part of your sample that is already transitioning to the next phase. So it's not like this metastable state is critically metastable until we stop the field, and then it starts to decay, but just by increasing the field, we're losing skyrmions on the way. But going back to that skyrmion that kind of lingers around, this is the intensity that we measured for this specific one, and you see that it starts at norm intensity starting at 1, it comes down to 4 for some reason over a certain amount of time, and then it goes down. We observe different types or several skyrmions that did this type of behavior. However, the amount of intensity of this middle level or this intermediate level was all around the place. So, well, one could first assume that these are chiral borders. Chiral borders should have a repulsive interaction with the surface. So you would assume that for a specific surface, they should be kind of around the same distance of the surface. And this is not exactly what we see. The statistics, of course, at this point, are not that high regarding this aspect. But we consider that probably pinning up the monopoles is a better explanation for the behavior we're observing. So going back to the decay of those two situations, when we decrease the field, we're able to fit that with just our normal exponential fit. We then obtain certain lifetimes as a function of this should be inverse thermal energy, and those can be fit to an array as well. So if we are close to the stability region, we obtain the energy barrier of about 109 MeV. If we go up in the field, the barrier goes down to about 13 MeV. For the helical decay, or for the decay into the helical phase, close to the stability region, we observe about 32 MeV, and in the region where we already decaying strongly, about 15 MeV. These are in qualitative agreement with their predictions that observe or that expect a strong independence of the energy barrier, as well as a higher energy barrier for the chemical phase than for the helical phase. However, if we take a look at this creep factor tau naught, there is this very, very large dependence on magnetic field. So this is not a magnetic field, but it's dependence on energy barrier, which is also dependent on the magnetic field. So it shows the same information. Instead of just considering the energy barrier, we consider the free energy. This creep factor tau naught can be or is connected with the entropy of the system. The entropy of the Skyrmion state with respect to a high excited state that determines the Skyrmion decay for any specific field. So we observe this large compensation effect, which leads to a decay rate of the Skyrmion even at very high energy barriers. And with that, I want to summarize my talk. So from the sense, we know there's logarithmic decay and strong asymmetric behavior from different fields, and we expect pinning. We observe probably the same type of pinning in the L-term, and the difference is in the L-term you can actually see exponential decay, strike the energies, and from that we observe large compensation effects that reduce the stability of the Skyrmion lines overall. And these are all my collaborators, and we welcome questions.
So the type of decay measured is always seen in superconductors for measure creep, and it's associated with glassy state. So
not really well. Yeah, the
this
type of
is
decay.
like
The type of decay is I don't think the type of decay is the important fact, right? That's the sort of dependent on different the parameters you're looking at the field temperature. What is important is this tau naught, and normally you would expect this tau naught to be in the range of about 10 to the power minus 9 or 8, something like that. And what we see is this strong dependence of the energy barrier over third magnitudes. And that's very uncommon. And it's, yeah, we're not certain where it's coming from in the case of these structures.
but you could use your data and analyze it in a glassy decay and
You mean the logarithmic data?
yeah.
Yeah. We've tried it, and the literature is sadly not really united as to whether it's okay to use the different stretch exponentials or different functions.
No, this is not stretch exponential, this is a logarithmic decay.
The problem with the logarithmic decay is that the logarithmic decay in the subconductors in the glassy system is an approximation due to the fact that we're not observing the whole decay region. And we have not enough data that we can actually make the same type of approximation. So at the time we're trying to let the decay be and try to see what the dependence on field and temperature might tell us about the system in the bulk state, especially since from the LP measurements, those two samples should be about the same from the bulk to thin film point of view.
Okay, so other questions? I have a related question. This tau naught is essentially the curvature of the potential railroad. Potential, from where this annihilation happens. So this means that somehow this is extremely strongly dependent on the energy barriers. It's surprising because it's the same system after all. Isn't it? So I can't help. But smart view of it. Further questions? I'd love to ask stuff. Even in the comments. So maybe just if you go back to this analysis of bubble versus non-bubble. So yeah, in this system, what would be the DMI period? Where would the bubble be?
That would be about, so you mentioned for about half DMI period, right? So it's, it should be about 45 minutes.
Okay.
So if we assume that the intensity goes with thickness, the thickness of the, so there's several assumptions that go into the intensity, right? So you will have to assume that the experiments are going to complete the sample, those are 230 nanometers, 45 plus, 0.25, 0.2. Yeah.
Because it's
If
still
you assume on both sides, then you should coalesce around 0.5.
and you have more statistics that you see here from.
So this is not the whole data on this type of case, but they have to be analyzed by hand. So this was just on about 30-35%. So the amount of times that we observed this is about 10% of all experiments that decay. So it's not happening all the time, but it's also not that rare. And yeah, we will need to look at more of the statistics to determine whether there's some kind of constant distribution. Sorry.
So, other questions? Don't see any questions. Other questions? Thank you very